Here system transfer function is given, and to this system transfer function the output is yt if input is unit step. So in the block diagram, and we have to find out the value of dy by dt at t equal to 0 plus. So to find out this, we will apply initial value theorem. First I will represent this system input and output. If to this system input is ut, this is system transfer function, the output is yt. So what will be the value of ys? Value of ys will be input transfer function, that is 1 by s into system transfer function this is the ys, which is Laplace of yt. Now to find out the value of dy by dt at t equal to 0 plus, we need to find out dy by dt is nothing but y dash t, and we have to find out y dash t at t equal to 0, or simply y dash 0. So to apply initial value theorem, we will first find out the Laplace of y dash t. So what is Laplace of y dash t? Laplace of y dash t will be s ys, where ys is Laplace of t yt minus value of yt at t equal to 0 plus. So we have the value of ys, and we have to find out value of yt at t equal to 0 plus. This is also represented as y0 plus. So first we have to find out the value of yt, the initial value of yt. So to find out the initial value of yt, we will apply initial value theorem to ys. So y0 plus will be limit s ys s tends to infinity. This is initial value theorem. So if you will multiply s here, you will get s minus 2 divided by s plus 1 into s plus 3. And if you will put limit infinity in the denominator, the degree of s is 2, and in the numerator degree of s is 1. So if you will apply this limit, you will get y dash 0 as 0. This quantity is 0. So you have to find s ys. So the Laplace of y dash t, this is equal to sys. If you will multiply s here, you will get s minus 2 divided by s plus 1 into s plus 3. Okay, this is Laplace of y dash t, and we have to find out the initial value of y dash t. So again we will apply initial value theorem. To find out initial value of this quantity, we will multiply Laplace of this quantity with s ys, s into s minus 2 divided by s plus 1 into s plus 3. Okay, first this s is multiplied to find out the Laplace of differentiated function, and this s is multiplied from initial value theorem, and here we will apply the limit s tends to infinity. So this will be s square minus 2s divided by s square plus 4s plus 3, dividing both numerator and denominator with s square. So you will get 1 minus 2 by s, 1 plus 4 by s plus 3 by s square. If you will apply s tends to infinity, these terms will be negligible. So the answer will be 1. Okay. The number and direction of encirclements around the point -1 plus j0 in the complex plane of S by the Nyquist plot of GS equal to 1 minus S divided by 4 plus 2S is. In this question, we are given with a function GS equal to 1 minus S divided by 4 plus 2S, and we have to find out the number of encirclement and direction of this point. Okay, the number and direction of by the Nyquist plot. So in Nyquist plot, what we do, the meaning of Nyquist plot is, in the S plane we have to cover the entire right half of S plane. So this is j omega axis, this is sigma real axis. We have to move this way, leaving the poles. We have to move this way, or in simple way we will move. This is j omega axis, omega equal to 0 plus 2 infinity, then making a radius of infinity here. S is equal to r e to power j theta. R tends to infinity and theta will move from, at this point theta will be 90 degree, 90 to minus 90. Okay, then from minus infinity to we have to move 0 minus, and then again making a half circle of, at this part we will have S equal to r e to power j theta. R tends to 0 and theta will tend to, at this point theta will be minus 90 degree to 90 degree. So in the S plane we will vary S this way, and in the plane of GSHS, by varying S, by putting all these values of S, we have to find out real part and imaginary part of GS, and those real part and imaginary part of GS will be plotted in the GS plane. Means here we will have imaginary part of GS, and here we will have real part of GS, and whatever plot we will get will be called Nyquist plot. So here we have to find out -1 plus the number of encirclement of -1 plus j0. Okay, so to find out the number of encirclement and direction, what we do for checking stability of any closed loop system, what we do when we find out the stability with the help of Nyquist plot. Let's say we have a closed loop system. We have a closed loop system here. To check stability of this system with the help of Nyquist plot, we draw the Nyquist plot of open loop system. So let's say we have a closed loop system, and for this closed loop system the open loop system is GSHS. This is open loop system of a closed loop system. So to find out the stability of that closed loop system, we form the Nyquist plot of this, and we check the number of encirclement of -1 plus j0, and we write this equation n equal to p minus z. How do we write this equation? Why we use this equation? To get answer of this question, you may refer the video lecture of Nyquist plot, the theory lecture of Nyquist plot, that has already been uploaded in on YouTube. Okay, and what is n? N is nothing but anti-clockwise encirclement. Anti-clockwise encirclement of -1 plus j0 in Nyquist plot of open loop system. So this is our open loop system, and for this system only we have to find out the number of encirclement and direction, and we are trying to find out the answer with the help of relating this question to the stability of a closed loop system. Okay. Okay, so if this is the open loop system, what will be the closed loop system? The closed loop system is nothing but 1 plus GSHS. The closed loop system will be 1 plus 1 minus S divided by 4 plus 2S. This will be 4 plus 2S plus 1 minus S divided by 4 plus 2S. This is S plus 5 divided by 4 plus 2S. This is 1 plus GSHS. Okay. This is 1 plus GSHS. Okay. Again, coming to this equation, N is number of anti-clockwise encirclement of minus 1 plus J0 in the Nyquist plot of open loop system, and P is number of right half poles of closed loop system, which is equal to number of right half pole of open loop system. The number of right half poles of open loop system and closed loop system is same. This we also observed in the theory lecture. Okay, so P is number of right half pole either of closed loop system or open loop system, and Z is right half zeros of closed loop system. Or simply right half zeros of 1 plus GSHS. Okay. So in the problem of Nyquist plot, or in the problem of stability with the help of Nyquist plot, we form the Nyquist plot. We have the number of n. Normally we have the number of right half poles, and we are mainly focused to find out the number of right half zeros of 1 plus GSHS. Okay, here we have a simple open loop system. So with the help of open loop transfer function, or with the help of GS, we found out 1 plus GSHS. So the number of right half pole is, what will be the pole of 1 plus GSHS? This is S equal to minus 2. This is a left half pole, and the 0 is Z is equal to minus 5. So this is a left half 0. This is not right half 0. So the number of right half 0 is, this is Z equal to 0. Number of right half pole is also 0. So N is equal to 0 minus 0. There is no encirclement of minus 1 in the Nyquist plot of this GS. So what I did, I related this problem to the problem of stability with the help of Nyquist plot. Normally in the problem of stability, you will be given with an open loop transfer function, but that open loop transfer function or the open loop system will not be as simple as given in this question. But in this question, this is very simple. So what I did, I found out 1 plus GS, and in 1 plus GS, it is clearly seen that number of right half 0 is 0, number of right half poles are 0. So we have P, we have Z, and we found out the number of encirclement. The another way to think is N is equal to P minus Z. This is a general equation, not only applied in the stability. This is a general equation. The number of encirclement, this is anti-clockwise encirclement. the number of anti-clockwise encirclement in the GSHS plane, this will be equal to number of right half poles minus right half zeros. If in the S plane you are moving in, you are covering all the right half of S plane, then this equation will be applied. And where you are moving in the right half of S plane only. So P will be right half poles and right half zeros. Now you have to find out, okay, the number of anti-clockwise encirclement of origin, not -1 plus j0, instead number of anti-clockwise encirclement of origin, that is 0 plus 0j. The encirclement of this point will be equal to number of right half pole minus right half zero. This is a general concept. If you are moving in S plane and in this closed region, whatever poles and zeros are covered, those number of poles and zeros will be appeared in this equation. The number of anti-clockwise encirclement of origin is equal to number of poles minus number of zeros encircled by or covered by this closed region. But we are interested to find out number of encirclement of -1 plus j0 of this plane. Okay, in the GSHS or in the plane of GSHS, we are interested to find out encirclement of this point. Now instead of solving for this equation, if you add 1 to this equation, if I am adding 1, the number of encirclement of G is the number of encirclement of -1 in the plane of GSHS will be equivalent to the number of encirclement of 0, since you are adding 1. So whenever in GSHS plane, in the plane of GS, whenever GS is equal to -1, if you will add 1 here, in the plane of 1 plus GSHS, you will get value of 0. What I am saying, in GSHS plane, whenever you will get -1 or whenever value of GSHS equal to -1, at the same point the value of 1 plus GSHS will be -1 plus 1, 0. So checking checking the encirclement of -1 of GS is equivalent to checking encirclement of 0 of 1 plus GS. Now we are checking 0 of 1 plus GSHS. We have 1 plus GSHS equal to 5 plus S divided by 4 plus 2S. Now we are checking number of encirclement of 0 of this. So we can apply this equation now. So N will be equal to number of right half pole. Number of right half pole is 0 because S is equal to -2. This is a left half pole. Here you have left half pole, and this closed region does not include -2. 0 is equal to, this is a pole, and for 0 you will equate this equation to 0 is equal to -5. 0 is at -5. Here you have a 0. So even this 0 is not included by this closed region. So the number of right half pole is 0, number of right half 0 is 0. So number of encirclement of 0, the number of encirclement of origin in 1 plus GS is 0, and number of encirclement of origin in 1 plus GS is equivalent to number of encirclement of -1 in the plane of GS. Okay, so here the answer will be 0. In this closed loop system, the open loop transfer function is given and the input is unit step, and in the output the condition is in the output we should have minimum settling time and no overshoot. Okay. In the output of a unit step function to a second order system, there should be no overshoot and settling time should be minimum. So in the second order system, the formula for overshoot is, or if the system is underdamped, we will certainly have an overshoot. Let's say this is the reference unit step. In case of overshoot, the graph will look like this. And in case of the underdamped system, in case of underdamped system only, we will have overshoot. And the condition for underdamped system is zeta must be less than 1. So if you don't want any overshoot, the zeta has to be greater than equal to 1. If zeta is equal to 1, this will be critically damped system. Critically damped system. And if zeta is greater than 1, this will be overdamped system. So if you don't want any overshoot, the zeta has to be greater than equal to 1. Now if I draw the response of a critically damped system, this is the transfer function of a general second order system. For critically damped system, this is the response, and this is for critically damped system, and for overdamped system this is the response. These are the response for overdamped system. So what we want, that the settling time should be minimum. The meaning of settling time is, this is the final value of output, the steady state value of output. If there is no steady state error, the steady state value of the output will be 1. Okay, in case of, and the settling time will be, if you will mathematically, if you will calculate the settling time, it will be infinity. But the practical settling time is, when the output is 98%, or in some case it is taken more than 98%. So practically, when output is 98% of the final output or the steady state output, we say that the required time will be settling time. So in critically damped system, the output will reach to its 98% value before than in case of overdamped system. So if you want, there is no overshoot, zeta has to be greater than equal to 1, and with no overshoot, if you want the system to be fastest or the minimum settling time, the system has to be critically damped. So we must have zeta is equal to 1, or formula for settling time is, 4 to 5 times of zeta into omega n. Let's say settling time is equal to 4 or 5 times the time constant, and time constant is equal to zeta into omega n. Okay, for detail you may refer the lecture of second order system. The time constant of system is zeta into omega n, and settling time is 4 times the time constant, 4 into zeta omega n. And if you want the minimum settling time, you have to keep zeta minimum. But we don't want any overshoot, so zeta has to be greater than equal to 1, and with this condition you have to satisfy zeta has to be minimum. So then satisfying this condition, the minimum value of zeta will be 1. Okay, so if zeta is equal to 1, now we have the value of zeta, we have to find out the closed loop transfer function. So what will be the closed loop transfer function? Kgs divided by 1 plus kgs. This is a unity negative feedback system. So k divided by s square plus 2s divided by 1 plus k divided by s square plus 2s. This will give you k divided by s square plus 2s plus k. And now if you compare with this equation, omega n will be omega n square is equal to k. So omega equal to root under k, and 2 zeta omega n equal to 2. It means zeta omega n equal to 1. So zeta equal to 1 upon root k, and zeta has to be 1. So k will be equal to, required value of k will be 1. And when the system is critically damped, this is the characteristic equation. This is a second order system, and when the system is critically damped, the location of, or the two roots of this equation will be same. The two poles of this system will be same. The value of two poles will be same. So if the two poles are same or the two roots are same, you will do b square minus 4ac has to be 0. 2 square minus 4k has to be 0. So k equal to 1. The two poles will be s equal to minus 1 and s equal to minus 1 only. This will be k divided by s plus 1 whole square. So k has to be 1. If we will draw the root locus of this system, the open loop poles are at 0 and minus 2. Okay, and this is the closed loop system. And if you, by varying k, if we draw the root locus, how will be the root locus? These are the two poles, open loop poles. These points will be on root locus because right to all these points the number of poles and zeros are 1 only. So these points will be on root locus. This will not be on root locus. This will also not be on root locus. So if you will vary the value of k, these points will move towards each other, and in middle there will be some breakaway point, and after breakaway one pole will move in upward direction and other will move in downward direction. This will be the root locus. So whenever before breakaway point the two roots are different and both the roots are real. Okay, so in this region, if both the roots are real, the closed loop transfer function will be written as k1 divided by s plus pole 1 plus k2 divided by s plus pole 2. Okay, and before breakaway point you have two real roots, so in this case the system will be overdamped. If you will draw the overall response of this system by taking inverse Laplace, here you will get k1 into e to power minus p1 into t plus k2 into e to power minus p2 into t, and if you will draw the overall response you will get this kind of response. And the settling time or the time constant will depend upon the response which is the slowest out of these two responses, or the settling time will be decided by the pole which is nearer to the origin. So before this breakaway point or before the two roots are equal, the one root will be nearer to origin than this point. So this will make the system slower. So to make the system fastest, what we need to do, the two poles must be equal, and when the two poles are equal, the system will be critically damped. This is the case of critically damped. And after this point, breakaway will occur and the roots are complex conjugate of each other. So in this region, the system will be underdamped or oscillatory. Okay, for this system, we have to find out the value of K, for which the gain margin and the phase margin, the gain margin is exactly 0 dB and phase margin is exactly 0 degree. In terms of gain margin and phase margin, how do we find stability? If a system is stable, we have gain margin in dB, this will be positive in dB, and phase margin will be positive in degree. For unstable system, gain margin is equal to negative in dB and phase margin will be negative in degree. And what is the third case? The third case, when the system is marginally stable or oscillatory. Marginally stable or oscillatory system. In this case, gain margin is equal to 0 dB and phase margin, this is not necessary to say gain margin is 0 dB and phase margin is 0 dB. If gain margin is 0 dB, sorry, phase margin is 0 degree, it is not necessary to say gain margin is 0 dB and phase margin is 0 degree. If gain margin is 0 dB, the system will be marginally stable and automatically you will get phase margin as 0 degree. These two things happens simultaneously. Okay, so we have to find out the case of marginally stable system or oscillatory system. So the best way to find out is form the Routh-Hurwitz table of closed loop system and make one complete row, only one complete row 0, and there should be no change in sign. In the Routh-Hurwitz table, for marginally stable system, what is the necessary condition? First, there should be no change in sign. There must be no sign change in the first column. Okay, and one and only one and only one complete row should be 0. So we will form the Routh-Hurwitz table for the closed loop system. So first find out the characteristic equation of this system. The characteristic equation will be 1 plus kgshs. The numerator of this equation will give you the characteristic equation. So 1 plus k divided by s plus 1 into s plus 2 into s plus 3. So the characteristic equation will be s plus 1 into s plus 2 into s plus 3 plus k. This will be s square plus 3s plus 2 into s plus 3 plus k. This is the characteristic equation. In S cube we will have 1, 11, and in s square we will have 6 and 6 plus k. This is s cube, this is s to power 1. Here we will have s to power 1, s to power 0. Here we will have, this is a, b, c, d. Here we will have b minus ad by c. So b is 11 minus 6 plus k divided by 6, 0. So we have to make one complete row 0. Here we will have 6 plus k. So we have to make this complete row as 0. Because this cannot be 0, we have to find out the positive value of k. So there is no positive value of k for which this term can go to 0. But this term can go to 0. So 11 minus 6 plus k divided by 6, this is 0. So you will find the value of k as 60. So when k is 60, the system will be marginally stable or oscillatory. If you will draw the root locus plot of this system, for k equal to 0, the location of closed loop poles will be equal to the location of open loop poles. The first pole is at -3, then -2 and -1. And the complete root locus will be these points will be on root locus, because right to these points 1, 2, 3 we have odd number of poles. This will not be on root locus, these points has to be on root locus, and this will not be on root locus. And the root locus plot will look like, and in the root locus plot, whenever a system is oscillatory, the location of two poles will be on imaginary axis. The value of k for which the location of poles are on imaginary axis, that value of k will make this system oscillatory, and another pole will be somewhere on the real axis. So to make this system oscillatory, the two poles has to be on imaginary axis. Let's say this is plus j omega and this is minus j omega. So this is a solution of this equation as 0. So this equation has to be divisible by s minus j omega. Similarly, this is also a solution of this equation. So this equation has to be divisible by s plus j omega. If this equation is divisible both by these two equations, so if you will divide this equation with product of these two equations, again you will get remainder as 0. It is divisible by this equation is also divisible by this, so this equation will be divisible by product of these two equations. The product will be s square plus omega square. So if you will divide this equation by s square plus omega square, you will get remainder as 0, or we have to get the remainder as 0. So if you will divide it, s cube plus 6s square plus 11s plus 6 plus k, s cube plus s omega square, you will get 6s square plus 11 minus omega square into s plus 6 plus k, then 6, then you will get 6s square plus 6 omega square. (11 minus omega square into s plus 6 plus k minus 6 omega square. Now the degree of remainder is less than the degree of s square plus omega square, so we will not further divide. this is remainder, and this has to be 0. Here you have s to power 1, so this has to be individually 0 and this has to be individually 0. So from here we will get omega square as equal to 11, and if you will put omega square as 11, by equating this to 0 you will get k equal to 60. So when k is 60, the system will be oscillatory, and the value of omega will give you oscillation frequency. Omega square is equal to 11, so omega equal to root under 11 radian. With this frequency, the system will oscillate when the value of k is 60. Okay, and the answer is 6 plus s plus 6. So whenever k is 60, the one pole will be at j root 11, another pole will be, the second pole will be minus j root 11, and the third pole will be s equal to minus 6. These are the location of 3 poles when the system is oscillatory. And if you will further increase the value of k after this point, the 2 poles will go to the right half, the system will be unstable. The asymptotic phase plot of a transfer function is given. This is frequency axis omega, this is 0.01 radian per second, 100 radian per second. This is 0 degree, minus 270 degree, this is minus 45 degree. This is asymptotic, or the asymptotic Bode phase plot of GSHS. This is given, and it is given that k and p1 both are positive, and we have to find out the value of p1. Then this phase plot, this is a straight line, and here what is the slope? This is 1 decade, and this is the 45 degree per decade, 45 degree per decade. Up to this point, here you have a change in slope. Up to this point to this point, you have a straight line, and the change in angle is minus 45 to 225, means 180 degree, and we have moved 1 decade and 2 decade. In 2 decade, the change in angle is 180 degree, so the here slope of change in angle will be minus 90 degree per decade. Here minus 45, minus 90 degree per decade. Here again you have a change in slope, and the slope is minus 45 degree per decade, and here there is no change in angle. Here the angle is 0. Okay, so to solve it, first let us remind what is the, if there is a pole P, what will be the Bode angle plot, or the asymptotic Bode phase plot for this transfer function. Let's say this is 0 degree, and the location of pole is here. Let's say this is 10. This is log omega. So the value of log omega will be log 10. Here you will get 1, or you will write omega equal to 10 radian per second. So when the value of s is equal to 10, or we will put s equal to j omega, and angle will be tan inverse omega by 10. So when omega is equal to 10 radian per second, when omega is 10 radian per second, the angle will be tan inverse 10 by 10. The angle will be negative, you will get minus 45 degree. Okay, here you have minus 45 degree. Then you will put high value of omega. If you will put high value of omega, very high value, this will give you minus 90 degree. And in asymptotic plot, the high value of omega is taken as the 10 times or 1 decade after the location of pole. So 1 decade after the location of pole will be this. Here you will have omega equal to 100 radian per second, that is 10 times of 10 radian per second. This will be taken as the very high value, or you can assume that when the value of omega is 10 times more than the location of pole, the omega will be taken as infinity. So this will give you minus 90 degree. So after this point, the angle contribution of this transfer function will be minus 90 degree. After this point you will get minus 90 degree. Similarly, a very low value of omega will be 1 decade before the value of or the location of pole. That 1 decade before means 10 times lower than the location of pole. So 10 times lower will be omega equal to 1 radian. So this is omega equal to 1 radian, or log omega equal to 0. So before omega equal to 1 radian per second, this will be taken as very low value of omega, or omega will be approximated as 0. Here omega is 0. If omega is 0, the angle contribution will be 0. So you have 3 points including the minus 45 degree, and you have to draw when omega is greater than 10 times location of pole, the angle contribution is minus 90 degree. When omega is less than p by 10, if omega is less than the 1/10 of location of pole, you have angle contribution 0. When omega equal to p radian per second, the angle contribution is minus 45, and you have to get the asymptotic plot. So this has to be a straight line. Meet these 3 points, you will get a straight line. So the slope will be minus 45 degree per decade. So the asymptotic Bode phase plot is, this is a straight line, and this will start from p by 10 to this will start from p by 10, and it will go up to 10p. Okay. This will start 1 decade before the location of pole, and it will go 1 decade after the location of pole. This will be a straight line. So effect of any pole in the asymptotic angle plot, effect of any pole in the asymptotic angle plot, this starts from 1 decade before and goes up to 1 decade after the location of pole. Okay. And whenever omega is greater than 10 times p, omega is treated as infinity, and if omega is less than 1/10 of pole, omega is treated as 0. Okay, now coming to question, we will divide this Bode plot in each decade, means from 0.01 to 0.1, then 0.1 to 1, 1 to 10, 10 to 100 radian per second. Here we have 100 radian per second, and this region will be less than 0 to 0.01 radian, and this will be after 100. So here you have 0 slope. You have a pole at 0.1. Okay, so effect of this pole will start from 0.1 divided by 10. Okay, So from 0.01 to 0.1, the slope has to be, here we will make the chart of slope. So effect of this pole will start from 0.01 to 10 times of this, 0.01 radian per second to 1 radian per second, and it will contribute a slope of minus 45 degree per decade. And before 0.01 there is no pole. Let's not talk about this right now. Let us consider only two poles. This is an unknown. Okay, so before 0.01 the slope will be 0, the slope is 0. Okay. Without consulting this pole, we will try to find out the slopes, and depending upon the mismatch between the slope, we will estimate the value of this P1. Okay, so before 0.01 we should get 0 slope, and we have a 0 slope. There is no mismatch. After 0.01 this pole will start contributing a slope of minus 45 degree per decade. Okay, and this will keep contributing this slope up to 1 radian per second. So between this range also this will provide minus 45 degree per decade, and up to 1 radian per, here also it will provide minus 45 degree per decade. Considering the effect of this pole, the effect of this pole will start from 10 by 10 means 1 radian per second, and it will go up to 100 radian per second. So the effect of this pole will start after 1 radian per second. So after 1 radian per second you should get minus 45 degree per decade, and from 10 to 100 also, up to 100 it is contributing, you should get minus 45 degree per decade, and after 100 you should get 0. Now where are the mismatch? Before 0.01 you have 0 slope, there is no mismatch. After 100 you have 0 slope, there is no mismatch. Between 0.01 to 0.1, between 0.0 to 0.1 you have a slope of minus 45 degree per decade. This is good, no mismatch. After 0.1 to 1, after 0.1 to 1 you have a slope of 90 degree per decade. Okay, and here you have a slope of 45 degree per decade. This part was okay, this part was okay, this part is not okay. After 0.1 you have a slope of minus 90 degree per decade, and here after 0.1 you have a slope of minus 45 degree per decade. So it means there is effect of another pole, and that pole will be P1. So what should be the value of P1? If you will put the value of P1 as 0.1, its effect will start from 0.01 and it will go up to 1. But you have to start the effect from 0.1 only, because after 0.1 only you have a mismatch. So to start the effect from 0.1, the effect will go up to 100 times. To start the effect from 0.01, the location of pole must be equal to 1. Okay. So if the location of pole is 1, it will contribute minus 45 degree per decade from 0.1 to 10. So first from 0.1 to 1, it will contribute minus 45 degree per decade, and from 1 to 10 also it will contribute minus 45 degree per decade. So overall in this range what you are getting, minus 90 degree per decade, in this range also minus 90 degree per decade, and after this again you are getting minus 45. So now we will have perfect match from 0.1 to 1. From 0.1 to 1 you have minus 90 degree per decade, and from 1 to 10 again we have minus 90 degree per decade, and after 10 to 100 we have 45 degree per decade. So the location of pole P will be at 1. This will be the location of pole. K is given as positive, so there will be no angle contribution of K. If it was given as negative, the angle contribution of this negative would be 180 degree. So we would add 180 degree in all the angles. So axis would have been changed.